Good evening, students. I'll start with the class. So previous class we had done the concept of work. Now today's is energy. Okay. See, whenever, like example, if I have to climb a hill, okay, work, example of work will be climbing up a hill, because you have to apply force on yourself just to climb. Okay. And then there's a displacement also. For climbing up a hill. So if you are asked to go and climb a hill, some of them may say, I cannot climb. Okay, I have no energy left. Maybe at some point you will go and then you will say, I can't climb anymore because I have no energy left. So how is energy related to work? So whenever I say I don't have any energy left to do the work, so energy is nothing but the capacity, your capacity to do the work. Whenever I don't have energy means I don't have the capacity to do that work. I'm told to climb a hill, but I say I don't have the capacity to climb the hill. That means basically I don't have energy. So the definition, okay. So in order to climb a hill, we need energy. The energy definition will be energy of a body is defined as the capacity or ability. You should be able to walk or able to climb. It's the same as work only, but it's just a different word expressed. Okay, body to do that work. To do work. So energy of a body is defined as the capacity or ability of a body to do work. So obviously unit also of energy will be same as work. So energy is also a scalar quantity. Okay, and its unit is same as work. That is joules or Newton meter. Okay, in terms of suppose CGS, then it would be erg and this would be dyne centimeter. That I've anyways given for work. It's the same thing, same as whatever is unit for work you have to use for energy also, because they are basically the same thing, just that the word capacity or the ability makes it look like energy. So definitely there will be various types of energies. Some of the examples would be like a sound energy, light energy in the form of light. It exists in various forms. Light energy, then nuclear energy, solar energy when it comes from the sun, atomic energy, okay, when it's from the elements. Hydraulic means water. Wind energy, various forms. Okay, these are just some examples. and also mechanical energy. So what we will be studying in detail is the mechanical energy. The two types of mechanical energies are kinetic energy and potential energy. Important thing to know is kinetic energy. Anyways, I'll be explaining in detail also, we'll be doing this, but just to remember what is the difference between potential and kinetic. Kinetic energy comes into picture only when the body is in motion. It has to move. If it is at rest, your kinetic energy will be zero. Okay. Potential energy should be at rest, okay, or it should be like stored at a height. Examples also I'll give you an individual, but it's like water tank. Okay, water stored in a tank on a building. So any height, if anything is stored, then it will be considered as a potential energy. It should not be moving. The moment you start moving, then it converts into your kinetic energy. So this is basically stored at one point. So if you leave that water tank and the water starts flowing, then definitely it is kinetic energy. First is the kinetic energy. There are many derivations under this. Then for the definition, so also indicated as K dot E. So it is nothing but the energy possessed by the body. Possessed means whatever is there inside the body. By the virtue of its motion. Virtue means when actually it's moving. This is important whenever whatever is the energy inside a body when it is moving. We want to know what are the examples. When a bullet is in motion after firing from the gun, moving hammer, or running water. Okay, or wind. Air is moving. That time you'll have wind. So that is why you have wind energy, because the wind is moving. Okay, various forms. Whatever is the movement will always have some energy. So basically the formula is, why is it has to be in motion? We'll derive also this formula, but before that, this is the formula for kinetic energy, half mv square. So it has to be in motion because this is velocity. If it is not in motion, so at rest what will happen? If the body is not moving, if it's at rest, v will be 0. So automatically ke will be what? Half m into 0. So overall kinetic energy will be 0 if the body is at rest. So only when the body picks up a speed, then only kinetic energy will come into action. So we'll do the derivation for kinetic energy now. Okay. Now in terms of diagram, suppose now if there is a body, suppose, which is at rest. Okay, just draw it on the surface. Obviously its mass will be m. Now this is at rest. Then what you do is you apply some force to it. So after applying some force, obviously this object will start moving and it may end up somewhere here, suppose, after moving. Mass will obviously remain same. Now it is in motion. Because of the force, it went from here to here, suppose. So that distance I'll consider it to be s. In which direction? Obviously it is going in this direction. Because force is applied, so it is going this side. It is picking up some velocity, obviously. Here initial velocity will be 0. Here it has picked up some velocity v in this particular direction. This is at rest. Huh? If you want to explain, now you have to start like this. Consider a body of mass m on a smooth horizontal surface. Now you can also write here and keep, this is for constant force we are doing a derivation for constant force. One more is there when the force is not constant. Constant force means if I am applying 10 newtons here throughout wherever till it reaches the end point, the force should be 10 newton only, it should not change. Constant force should be applied. So that is the derivation what we are doing for constant force. So we have to write there, let constant force F act on the body hence what will happen the moment you apply force, body gets displaced to distance s. Okay, you can write in your own words also if you forget. If you apply a force, then the body moves for distance s also. You can. So u is your, let u be the initial velocity and v be the final velocity. At rest, remember u equals to 0. Final velocity is v. So now basically what we know, we'll calculate what is the work done. Work done, you know that is it is force into displacement. Okay, W is this. So this formula we have already studied. Looking at the diagram, okay, force side applied this side, displacement is also this side, they are parallel, both of them are in the same line. Okay, okay, displacement is also in the same line. So any two parallel lines in the same direction, theta is always 0, I told you. So force you can write in the bracket and keep is parallel to s or in the same direction as s. Okay, so theta will be 0. So that's why what you'll get, cos of 0 is just F into S. So mark this as equation 1. This is a work formula, fixed formula it is. Now we'll calculate what is the acceleration. So if A is the acceleration, obviously if the body is moving, it will have acceleration. A is the acceleration, then what is that? You know that force is mass into acceleration, this formula. This also everybody knows, force is mass into acceleration. Mark this as equation 2. So what all we wrote, you know, what is work done, what is the force acting on the body, and using one of the kinematic equation, three equations we know. U is equal to this AT, this equals to U plus half AT and all that. So we'll just use one of them. We, in terms of displacement, V square will be equals to U square plus 2AS. The other one was S is equals to U plus half AT square. But time we don't want because we are not dealing with time. We want to use this equation. This we can't use because time we don't know. So this is the best option. We know initial, we know final velocity, acceleration and distance. So substitute the values. Obviously U is 0 and they are just written at the starting of the derivation. So V square will be equals to 2AS because 0 anyway is gone. So what is the distance? S will be, bring this down. This is equation 3. So we got the value of C. Basically, we have to calculate the work done. We know what is F and we know what is S. So we'll put the values of F and S in this equation. So put values of F and S from equation 2 and equation 3 in equation 1. So this and this you have to put it in equation 1. So you know that work is nothing but force into displacement. So what did we get? Force as mass into acceleration from equation 2 into M. This A and A will cancel. So whether I write upon 2 or multiply by half, it means the same. So work done is equals to nothing but to kinetic energy. I told you always, it's just work and kinetic energy is almost same. When okay, so instead of work, you can also write it as kinetic energy. This is the derivation for kinetic energy. This was when the force was constant. Now suppose the force was changing all the time. So whenever there is a variable force, integration will come into picture. We have already done one derivation in the previous class. Same way we have to derive here for kinetic energy. When force is variable. Previous one was when it was constant. In the previous class I had explained to you, whenever any force is suppose variable like this, what we usually do, we always divide this into very small strips like this. It just okay like this. Everything will get divided into many strips. And this one strip, this is always equals to ds. ds means small distance s. So whenever I'll be using this, so basically it means small delta. Okay, small distance, because a very small strip we are taking compared to this entire s. Same way, whenever I'm calculating area for this one now, it will be, I told you, area under any curve, that much area is always the work done. Force, this will be force, this will be s. Okay, so force in length into breadth, so it's like force into the distance will always give me the work which is done under this. So that work also will be very small, that would be dw for that particular area, small work because small distance. Okay, so you can start like this. If variable force x on the body and total displacement is s till the last one, what we do is we divide the kinetic energy of, in order to find the kinetic energy, we divide the total displacement, total distance. Okay, we won't use the word distance because it's as displacement. We divide it into small strips, I also called it small segments, into very small segments of length ds. No need to draw the diagram, huh? This is only for your understanding I've given. Its small strip length is ds. Therefore, small work done will be how much? Small work done will be dw. This w would be for entire this from starting to end point, but dw would be like for that small strip. Therefore, total will be is nothing but, I told you, integral means it's like adding all the small strips till the last, from starting point till the ending point. There is nothing but some adding all the work. So this is the sign. So you can mark this as equation 1. Also we know that what work done, also you can say work is nothing but force into displacement. So for small work, what it will be? Okay, basically for small work will be force into small displacement. If I want to calculate small work, then it will be small displacement. So that will be dW will be equals to F into ds. Now we'll see what is force. Force we know that is mass into acceleration. And also we know that what is acceleration? Change in velocity upon time. Acceleration is nothing but change in velocity. No need to write this. This is only for your understanding. Upon change in time. Okay. Acceleration is what? Final velocity minus initial upon time. We always do that. So what we'll do, basically substitute it here. What is the value of A? dV by dt. So force will be M dV by dt. Put this as 2. We can put this equation as 2. And this as 3. So what I'll do, I'll put the value of F over here. So put value of F from equation 3 in equation 1. Sorry, in equation 2. Yeah. So dW will be equals to M dV by dt. Wait, the announcement. I just mute for some time. dW will be equals to F M dV by dt. Okay, put this value over here. And then this already is there, that is ds. So I put the value of F over here. So equation 3 I have to put in equation 2. Now what I'll do is, I'll just shift this here. V I'll bring this side, S I'll bring this side. I'll just exchange these two letters, okay? So S I'll bring this side, V I'll take on the other side. So I'm exchanging these two letters. Can anyone tell me what is change in distance upon time called? What is change in distance upon time?
Speed.
What is final distance minus initial distance upon time? Basically, what is distance upon time?
Speed.
Speed. But in terms of displacement, what it will be?
Velocity.
Yeah, velocity. So this is nothing but, so we know that ds upon dt is nothing but change in displacement. D means a small displacement upon time, which is basically equals to your velocity. So dw will be mv dv will. So mark this as equation 4. So now put the value of this dw in equation 1. Put value of dw from equation 4. This all this you don't have to write in detail for exams and all. Just put equation 4 in equation 1. So what was equation 1? This was my equation 1. So just put everything here. Okay. In order to write the limits, starting and ending point, this is with respect to v. Okay, velocity. So what, this is always the starting point and this is always the ending point. So starting velocity was 0, ending velocity was v. Basically it's nothing but u to v, but u is anyway 0. Okay, if you want you can write one more step. Otherwise it's like basically work done is from starting till the end of the velocity, but u anyways would be 0. So this is 0 and this is v. M is mass. Mass is a pure number. Any pure number will no need to integrate that. We can always bring him out. Same like for derivative. This no, any coefficient is there, we can always bring him out of the integral sign. And v is there. So it's basically like 5 times x I have to integrate, and this would be dx. So this 5 you can always bring out, and then x dx like this. And in the previous class I given you the formula, integral of x raised to n dx. These letters will always be the same. Okay, if this is s, this will be s. If this is t, this will be t. Then the answer is what? X raised to n plus 1 upon n, and then you have to put the limits. If it is from a to b, this will be from a to b. So applying that integral formula over here, what is the power here right now? 1. Basically the power is 1. So what will I get? V plus 1 upon 1 plus 1. So it's m times v square upon 2, 0 to v. So first what you have to do, I told you, you have to always put the higher limit substitute here first. So wherever there is v, you will have to put it as v only now. The same value will come. If it was some other number, no, like suppose if it was in a problem like 0 to 3, 3 would come here. That way. Higher limit you have to always substitute first. So as per that logic, m is anyways out. So this will be v square upon 2 and minus 0 square upon. Then we have to put the lower limit wherever there is v. So anyway, this is gone. So W is nothing but half. Okay, it's not. So you know that this work done is equals to kinetic energy. So kinetic energy will be equals to half mv. Both the ways will get the same answer, but the way to solve will be different based on whether it is constant force or variable force. So these are the two ways you can derive the based on which kind of force is applied. Now, how can we prove that work and energy equivalence means whenever I'm saying work is same as energy. If I did not have that power backup, by now see how much time would have got wasted for current to come. Okay. So basically before proving, we can also say that work done is nothing but change in kinetic energy. Okay, it's nothing but like work done would be final kinetic energy minus initial kinetic. How it means is like suppose you have some body M at rest. Okay, this is suppose at rest. Then what I'll do, I'll just apply some force on this. Or maybe if it's moving starting at U, suppose if it's having some initial velocity U, then apply some force. So what will happen whenever I apply some force, it will get some extra boost. So it will start moving. So obviously this U will change into V. Suppose if it was going at 10 meters per second. And if I apply force, it might go at 15 meters per second because it's giving in the same direction as the movement. Okay. So it might get displaced here with another one. So that would be M. So as per the logic, what it will be, first kinetic energy will be your M, this half mu square your kinetic energy will be half mv square. So total work done would be what? This minus your kinetic energy, final minus initial. We'll prove this. There's one derivation. So this diagram only you can draw. No need this. Okay. So the derivation, I'll write a topic first. Work energy equivalence. So it would be like the diagram. Textbook might not give you the diagram, but only for understanding point that there is one this body which is moving at velocity u, then there's a force applied, and then the velocity is v. So what does work energy equivalence state that? It states that the work done by the force acting on the body is equals to change in the kinetic energy. So basically this is nothing but, I have already given, work done is nothing but final minus initial kinetic energy. This is what it basically means. Change in the kinetic energy. So how to start about it? Let consider a body of mass m with initial velocity u. Then what we'll do? We'll apply a force. Force F is applied. Therefore, object or that body displaces, body changes its velocity to v. And gets displaced to distance s. So it was having some initial velocity u, then you applied some force, then it got changed to a different velocity and moved to distance s. Okay. Now this is not specified. It's a constant force. So we'll have to do it using normal this only. So what we know is work is nothing but force into displacement. So this work is nothing but same like your previous one. It's all the total work done. Total means what? Addition of all the small works will give you the total work. Therefore, small work done also can be written as force into displacement. Same like the previous one. Same derivation it is. Only thing now it will be from u to v. That's it. That was where in the previous problem the body was at rest. So that's why u was 0. Over here we cannot take u as 0 because we are not taking it at rest. We are assuming that it was already moving at some initial velocity u. But this equations will remain the same. So this was 1. Then GW is F into small displacement ds. Okay, straight away we can write F ds. Then what we wrote? We know that force is nothing but mass into acceleration, and we wrote it as acceleration is nothing but change in velocity upon time. So what I did, acceleration I had put here. Okay. This I kept it as 2, I think, no? This was 3. Okay. So put value of f from here to here. This value you put here. So dw is nothing but f ds. So f is what? M dv by dt. So basically the value of f I have to put here. I just wrote that equation again. This was equation 2, I just wrote it, and whatever is the value of 3, I put it there. Then what I had done, I had exchanged this. V will go out, S will come here. dV I brought out. And this, I told you, change in distance upon time is nothing but velocity. And now final, put 4 in equation 1. So substitute the value of dw. So what was work done? Integral of dw. So put this all here. Integral of mv d. Then this is power 1. So straight away. Okay, now the what will be the signs? Work done. You have to take from u to v. Here also you can write, no issues. Now we cannot take u as 0 because the body is not at rest. So this will be m, I'll bring out because it's a constant. Derivative, the integral of v dv is v square by 2. That power 1 plus 1 upon 1 plus 1. So straight away you can always remember integral of x is always x square by 2. So no matter what is the letter, we just have to increase by 1 power. So integral of x cube would have been, suppose, x raised to 4 upon 4. Just have to raise 1 power extra, and that same power you have to write down. So if this power was 1, so it just becomes square upon 2. And this is m anyways is out, u to v. Now put the higher limit first. And then put the lower limit. So now open up the bracket. This will become mv square by 2. So work done is nothing but, if you notice, this is your final velocity, final kinetic energy, and this is your initial kinetic. So which we have proved. Work done is nothing but final minus initial. So if the body is starting from rest, no, u will be 0 and this will be only part. Okay. So this was about kinetic energy. Next is potential energy. It is nothing but it is the energy possessed by a body by virtue of its position. Position means at one position only it was not in motion. For kinetic energy, it was in motion. This is at one position. In a field of force. Means some force is trying to pull it down. Okay, whenever you are keeping this water tank, no, anything you keep at a height, definitely there will be mg. Okay, the field of some force will be there, but it is still storing something. So this what is the inside will be a potential energy. It has to be definitely at a height, huh? Compulsorily it is at should be at a height. Suppose if I'm holding any ball in the hand on top, obviously it will be holding some potential energy. But if I keep that ball on the ground, okay, okay, before that I'll just give you what is the formula for potential energy, then it will be easier to understand. We'll prove this also. Before that I'll just give you the formula. Potential energy is nothing but mgh. G is the gravity due to acceleration. This acceleration due to gravity. This is what? Height. M is the mass. G is acceleration due to gravity of Earth. H is the height. Now, if I keep some box at a height from the ground, okay, definitely there will be a force mg acting on it, and it is at a height. Okay, so it holds true. But suppose if it is straight away, this box is at a ground. So in this case, height will be 0. So what will be potential energy? 0. So you can never say any block or any ball with that water tank, no? That same water tank which is on your building, if you keep it on the ground, on the earth, it will not be called as potential energy because the height would become 0. So remember that way. So any applicative question is asked, like if a ball is kept on a surface of the earth, would it be holding potential energy? Definitely not. Why? Think of the height. So this is very important. It should be at a height.
Please, can you explain again?
See, if this is the earth, so height is always referred from the, okay, height means distance from the ground, from surface of earth. Here definitely height is there because I'm, okay, ground or earth, whatever, the same ground. Here if I'm keeping it at a height, I can say this has potential energy, that is what? M, G and H. Okay, but here I cannot say this has a potential energy stored in this. This water might be there in this, but I cannot say this has a potential energy because my height is 0 with reference to this. It acts only when it is raised at a height. Okay, even if you slightly raise it, then it will have potential energy. Like there should be some height, but if the height itself between the earth and the this is 0, the potential energy overall will be 0. So does it, this block or this water tank, does it hold potential energy? No, no potential energy, because as per the formula itself you come to know height is 0, so potential energy is 0. So any potential energy will be considered only if that object is raised at some height from the ground. Now understood?
Yes, miss.
So we'll prove that formula. No. Yes, this is suppose on the earth. Okay. Obviously mg is acting, but in this case height is 0. So potential energy won't be there. So in order to calculate, what we'll have to do, I'll have to raise it to some height. Okay, I'll have to first raise it to some particular height. Because I'm keeping it somewhere here now, compared to the ground. So this might be the ground. Now I've raised it. Now, how much minimum I would need is like to lift it up. If this much 10 Newton is this, no? So exactly either 10 Newton I would need it to this, or more than 10 Newton. So if this side it is mg, then on the opposite side I'll have to apply more than mg, okay, or exactly equals to that or more than that to take it up. Okay, so again this force I'll have to apply and take it up. The same thing would be applied over here. There's this force which is acting downwards here, mg, and this is the height which is this raised to. So this point A you can consider, this will be at point B. So you can name this as gravitational potential energy. So consider a body of mass m lying on the surface of the earth. Okay, at point A, acceleration due to gravity, or you can name it as g is acceleration due to gravity. Therefore, weight acting vertically downwards will be, how much will be the weight acting on the body? Mg. Now, in order to lift the body, of course, mg is applied in upward direction. In order to lift this body up, of course, mg is applied in. Okay, so let h be the height. Or I can write in simple words. This looks complicated. Height through which the body is lifted. Body is lifted to height h. Now work done, we'll see how much of work is done. Work done in lifting the body. This was weight, don't get confused with this. You can write it as weight only and keep that W might be confused with work. Okay, that work is different. So just write it as weight is M. This work done only is W. Work done is force into displacement. Anyways, height means it's going upwards. Which side I'm applying the force to take it up? This side. Height, I'm taking it upwards. So both are in the same direction. So theta is 0 because both force that is equals to mg I'm applying and height also is going up. Same direction. Whenever force and displacement, this is nothing but a displacement, no? Height. So both are in the same direction, parallel, so theta will be 0. So W is Fs because cos 0 is 1. So what is the force which has been applied to take it up? Mg. What is the displacement? H. So we have seen that work done is nothing but potential energy, any kind of energy. Right now it is stored, so it will be potential energy. This work, whatever is done, is stored in the body. Body is gravitational potential energy. So this is of work, nothing but energy. The capacity, how much you did and stored in that is nothing but m into g into h is mgh. This is the derivation for potential energy. Next one. Suppose if we have a spring, what would be the potential energy? Okay, before that, I just suppose if you have a spring, okay, so what will happen if I'm suppose stretching it? And keeping it holding, okay, so what will happen? This is storing some energy. Why? Because when I leave it, it has to come back. So whenever I'm pulling it, there is some displacement, okay, and definitely it's not on the floor, it is at some height. So if I'm pulling, okay, it will always be having some potential energy stored in it. Now the moment I leave the spring, okay, so right now I'm holding it, but if I open this, it will come back to its original position. Okay, first what happened, I stretched it, so obviously in the opposite direction it will have some restoring force, that is negative F. It always wants to come back. So how much ever you have applied your force to pull it, so it will have a restoring force. From where does this get its force? It stores its energy and then it tries to come back to its original position. So while coming back, it is kinetic energy in the motion, but whenever it's in the like the stretched form, so this is called as a stretched form. So it will have some kinetic energy, this potential energy stored. Then it will come back to original. Same way, if you are compressing a spring, that would also, okay, if you are pressing the spring and making it like this, so which side you are applying the force to compress it? This side. Which side would be a restoring force? Opposite side. So this also will have some potential energy stored in it. The moment you leave the spring, then it will get converted into kinetic energy and go away and come back to its original position. Okay, so this is how it works for a spring. So whether you stretch the spring or you compress the spring, okay, make it small or make it large, in both the cases it will store energy. The moment you leave the spring, it will go back to its original position. This I had explained under the previous chapter. That was under friction, I think, that time. The potential energy of a spring. So when a metallic string is stretched or compressed by a force, whatever work you do, work done in stretching, either you stretch or compress or compressing the string is stored. It gets stored, okay? Whatever work done is stored in the spring in the form of potential energy. Only when it is stretched or compressed, not when it is in its original position. Otherwise, it would be in its rest position. But when you are stretching it or you are compressing it, that time only. Because there has to be some force applied. Otherwise, there is no point. So for the diagram, what you can draw is suppose if I have a spring at point C. Now what I'll do, I will stretch the spring. Maybe to some distance, that is till P. From C, I'm pulling it to P. And after P, again little bit small distance, I'm stretching it to Q. Very small distance, huh? From P to Q. This was P, this will be Q. And the small distance, you mark it as dx. Instead of S, no, they have used the word x as in the derivation. Okay, so that's why I'm using x only. For distance S, no, they have used the letter x. So instead of ds, it would be dx. No? So what have I done? This was the spring. First I stretched it to this place, point P. In very small distance Q also I stretched it little bit more. Okay, very small distance dx. So this is the diagram. And which side will be the restoring force? Opposite side, because I'm stretching it. So this is F is the restoring force. I'll mention it. I'll write the theory part. So this is the diagram. Everywhere it's trying to come back. Okay, so consider elastic spring firmly fixed means tightly fixed. You can say O at one end, O, and other end is attached to a block, this block of mass M. When block is pulled, now you're blocking, pulling the block from point C to point P. I'm pulling the block from point C to point P. Automatically, the spring will also get stretched. Okay, so let me take this distance from C. This would have been the original distance. Let that be X. This distance, okay, from C to P. Now, what will happen? Due to elasticity of the spring, I'll erase the diagram now. Due to elasticity of spring, there's a restoring force. Minus F. Why? Because it is in the opposite direction. Okay, or I can say restoring force acting on the spring. And this restoring force now is directly dependent on how much you stretch it. This force is directly proportional. The more you stretch the spring to a more distance, definitely it will need more force to come back. Okay, the more distance you are stretching the spring, definitely more will be the force needed. So it is directly dependent. What is this sign? Directly proportional means force is dependent on how much distance you are pulling the spring. So if I want to remove the proportionality sign, you can use it as minus K. Why negative? Negative K because restoring force is negative. Is opposite to the displacement. Force is acting this side and spring is getting stretched this side. So that's why it is negative. Further, now what you are doing? Further block is stretched to very small distance dx. Okay, from P to Q. So small distance, if you are stretching, definitely there will be small work done. Force into small displacement. How am I getting this? You know that work is force into displacement. So small work will need small displacement. So small displacement will create small work. Small work done means dW, and this is ds. No, sorry, not s now, x. Okay. Now this force, you can directly take it as k times x only. You can ignore the negative sign while calculation of work, because we don't say negative work and all that. No need to mention that. We are just calculating how much will be the energy stored. So energy, we will not say negative energy stored or positive energy stored. We can just ignore the negative sign and just put it as kx. Force is nothing but kx. And from equation 1, okay, that force is minus kx. We can mark it as equation 1. From there, put the value of force as kx. Now total work done will be how much? Integral. So put it here. What is dw? No, kx dx. That previous this no derivation, this was v dv, means velocity. So we used to put velocity limits here, but this is x distance here, so we'll have to put distance limits. So from original we are starting and then stretching it to x. So this would be like 0 to x. K, you can bring him out. Now integrate x, so power is 1. So obviously it will become 2 upon 2. Then put this here, 0 to x. So put the higher limit first. So x will remain as x only. Lower limit will become 0 square upon 2. Wherever there is x, you have to put that value. So this will anyways go. So this work done is stored as potential energy. Sometimes they use this letter U, potential energy in a spring. Not if your teachers don't use, leave it. But this is main thing. Kx square upon 2. So this is the potential energy for a spring. And one more thing is left, just conservation of this, of a free mechanical body, that I'll do, and then energy part will be over. Next class I can start with power. I'll just finish off that. Conservation of mechanical energy of a freely falling body. What does conservation of this it mean? As per that, the statement is sum of kinetic energy, sum means total, and potential energy of a freely falling body is constant. Constant means same throughout at all the stages. We'll prove that also. Means what? If there's a box, okay, Ke plus P will be same here. When it starts falling, in the middle also we'll calculate what is that Ke plus P, and after reaching almost to the ground, when it reaches, then also we'll calculate and see what is the total this. Everywhere this will have same value. So energy always, total energy always remains the same throughout the body whenever it is falling from a height. That is what we will prove. So quickly draw this diagram. So initially it is at some height. The initial velocity is 0. Then you drop it. So in the middle it might reach at some velocity. Okay. And then one more towards the ground. Total height will be h from here to the ground. Now from here, suppose if you are holding somewhere here, this distance, let it be x from here to here. So from here to here is x. How much will be from here to here? So if this was suppose 30, this total height was 30 and this would be 10. How much would be this? 20. How do I get 30 minus 10 would give me 20. So it's nothing but h minus x will be this height. Total height minus this. Okay. So this is at point A. This fellow is at point B and at point. So at the three stages, we will calculate the kinetic and potential energy and show that it is same everywhere. At point A also, B also, and C also. Consider a body of mass m. At point A, at a height h from the surface of ground. So first we'll calculate some of the potential and kinetic energies at point A. So I'm starting this at point A. So what all data I know? Height is h, velocity is 0, mass is m. Why? Velocity is 0. We are starting it is at rest. Starting and then we are dropping it. So we'll calculate the kinetic energy first. What is the formula? half mv square. We know that it is 0. So kinetic energy I will get 0 at point A because velocity is 0 at point A. I'll calculate the potential energy. Potential energy is full because it has height also, and definitely gravity is acting on it because it is at a height. So nothing is 0 here. All values are there. So that is your potential energy. So add both of them. So total energy I have to calculate. Total energy is nothing but kinetic energy plus potential energy. So just add 0 plus mgh. Total energy at point A I am getting is mgh. Mark it as equation 1. Now let me calculate at point B. Point B. Height is now what? From the ground at point B, h minus x. Okay, at point because this is from ground we have to measure, huh? Not from up. From the ground surface at how much height is that at point B? So it is h minus x. Mass anyways this is same, m, and velocity is v now, not 0. So let us calculate kinetic energy in terms of gravity. We will have to write, okay, because this has nothing in terms of distance and all calculate. So what I'll do for kinetic energy, we know we'll use the kinematic equation. But v square is equals to u square plus 2as. We know that the initial velocity where it started would be 0. This velocity is v at that point. Acceleration due to gravity would be this. Okay, this one's okay. This distance for kinetic energy. See, 1 second. Huh? This is for kinetic energy is falling from this side. Potential energy is always referred from the surface of the ground. So this you write for potential energy. Whenever we calculate height for potential energy, always we refer from the surface of the ground. But for kinetic energy, see now the body had started falling from here. So where it started gaining the kinetic energy from here, because this was stored in some form of some potential energy. Then it started flowing till where it reached. This was the initial starting point. Here it ended. So this distance would be x for the kinetic energy. Okay. So this is the distance covered asking, not the height. So try to understand. So distance is right extra thing. So distance covered by the body is x and height is this. So that's the difference. Huh? So this s is nothing but the distance. That would be So with this velocity I was calculating. What is the value of v square? 2gx. So just put the value here. What is the value of v square? The kinetic energy is half m. Put this value, v square is 2gx. So 2 and 2 will cancel. So kinetic energy I am getting as mgx. I calculated the kinetic energy at point B. Now we'll calculate potential energy. This was for kinetic. Now potential. That is mgh. Height is how much? This h means height. So how much is the height at point B? H minus x. Now add total energy. This is how much mgx I got. Potential energy I got at h minus. Now open up the bracket, multiply this both inside. Finally, I'm getting a mgh. Mark it as equation 2. And now final one, that is point C. See, whenever we are calculating final, no, not that after it stops, just before hitting the ground, it still has that velocity v. Don't consider it reached there and then it became 0. Just before hitting the ground at point C, velocity is still v. So kinetic energy is half m. Okay, before that, height is 0 because it has almost reached the ground. Then mass is anyways m. Velocity is v. Now distance covered by the wall from here to here, from starting to this distance s will be h now, because from here to here he reached the ball. So distance covered is h now. We'll calculate kinetic energy. So we have to always calculate this v square. So same like the previous time, we'll use the formula v square is u square plus 2as. U square is 0, starting initial velocity. Now s will be how much? H. So v square value is 2gh. Put this value here. Put the value of v square in this equation. So how much you'll get? Kinetic energy is half m. Instead of v square, I'll put this value 2gh. So 2 and 2 will cancel. Okay. This is the kinetic energy. Now let us calculate potential energy. but now here height is 0. For potential energy, the potential energy will get as 0. So add the total energy, kinetic energy plus potential energy. So if you see equation 1, 2 and 3, at all the points when you added all the energies, it turned out to be mgh. So write the final, therefore from 1, 2 and 3, sum of kinetic energy and potential energy is same at all stages. Therefore, total energy is conserved. It is not lost anywhere. It remains the same. Conserved means not lost. Okay, so this was all about the energy. Last sentence, principle of conservation of energy. This everybody knows. Energy can neither be destroyed, okay, nor created. Okay, it states that energy can neither be created nor it can be destroyed, but can be changed from one form into another. Energy, okay, it states that energy can neither be created nor it can be destroyed, but can be changed from one form to another. Into another. Okay, so with this we finish with the energy part. Then next class I'll start with power. I'll stop here.